Hello and welcome to this lecture. We're going to start looking at the topics of Bayesian estimation and maybe a little bit of hypothesis testing. We'll get started this week. So this is a different way in which the estimation problem can be solved. So you remember we are looking at IID samples according to some distribution which is parameterized by some unknown parameters theta. We are trying to come up with an estimator given the samples. How do you find some estimation for these unknown parameters? How do you come up with some values for these unknown parameters? There's some very interesting methods that we saw. We saw two methods. One is method of moments. The other is maximum likelihood. We will see in this lecture the next very popular method, which is Bayesian estimation. Okay, so we'll take a quick introduction at it and come up with ways of deriving these Bayesian estimators. Okay, so Bayesian estimation is first we start with. So we've been looking at this problem of point estimation or estimation of one unknown parameter given samples from IID samples from an unknown distribution. Okay, so there are so far we saw some estimators. It turns out there are two ways of thinking about design of estimators. One is what is called the frequentist approach, where you treat theta as an unknown constant. It's a constant, and you have methods like method of moments, maximum likelihood. There are various other methods associated with the frequentist approach. The next approach is where it's called Bayesian, where you treat this theta as another random variable. Okay, so remember we are already parameterizing the samples to come from a distribution, and it has an unknown parameter theta. Now we will think of theta itself as another random variable in the Bayesian approach. Okay, so once you say random variable, I have to think about its distribution, right? So that distribution we will assume. We'll assume some distribution for theta. That kind of a setting is called Bayesian estimation. Okay, so remember the frequentist one is where theta is assumed to be constant. The Bayesian one is where the unknown parameter itself is assumed to be a random variable. There's different, these are two different schools of thought. There's lots of debates between these two philosophies of designing estimators. But as far as we are concerned, it's one more approach. As long as it gives us an estimator, why not, right? So we'll take it and we'll see what we can get with it. Okay, so I'm going to begin with an example and sort of motivate how to think about this kind of Bayesian approach. Okay, so far when we think of samples from say a Bernoulli distribution, Bernoulli P, IID Bernoulli P, it's a very common distribution that occurs quite often. We always thought of P as some unknown constant. It is some value between 0 and 1. I don't know what it is. I'm trying to estimate it from the samples. Now in the Bayesian setting, you will start with some distribution for P. So for instance, you will say here is some distribution I'm assuming for P. I'm saying P is going to be uniform and it takes only two values, 0.25 and 0.75. Okay, so how do you think of this? You have to think of it as there is a collection of coins of you're tossing a coin to get the Bernoulli distribution, right? Heads is 1, tails is 1, heads is 0, whatever. I mean, so that way you're tossing a coin to get the Bernoulli distribution. There are two sets of coins, some coins in one pot, another coins in another pot. The coins in pot 1 have a probability of heads which is 0.25. The coins in pot 2 have a probability of heads which is 0.75. So this is a typical Bayesian setting, right? Earn 1, earn 2, so many coins. And then I'm going to pick one pot and then I'm going to pick one coin from that pot. So I may get a coin of probability 0.25 or I may get a coin of probability 0.75. I don't know. So I'm picking up that coin and then I'm tossing. I'm telling you what samples I observe. Okay, so this is the sort of Bayesian setting which should be in your mind. Like the parameter, unknown parameter is not something that is some constant which I don't know. I'm going to think of it as coming from some probabilistic experiment. Okay, so once you do that, you do the Bayesian, you're in the realm of Bayesian estimation. Okay, so what do you do with this knowledge? Once you say P is uniform, here are samples 1, 0, 1, 1, 0. I will use this notation for these samples, right? So notice there are 5 samples, 1, 0, 1, 1, 0. Remember once again, what is the experiment? There are 2 types of coins. I'm picking one type uniformly at random. I could have a 0.25 probability of tails coin, or a 0.75 probability of tails coin. So I may have both of those, and then I'm tossing this coin repeatedly. Let's say I toss it 5 times, I got 1 0 1 1 0, right? So this is 5 samples from the Bernoulli distribution. So to denote this event, remember this fact that samples are 1 0 1 1 0 is actually an event, right? It's some exact event that happened in your sampling. So what is that event? If you want to write it down properly in terms of the random variables, that event S, okay, so this is an event, okay, this is an event, okay, and that event S I'm going to call as x1 equals 1, comma x2 equals 0, right? So this is the first sample, this is the second sample, and so on, right? So I got 5 samples. I wrote out that event in some detail. So this notation is useful for us. So remember this notation, S is basically the event that you observed these samples, right? So that's the S event, okay? And we will estimate using Bayes rule. So we have this 2-stage probabilistic experiment. In the first stage you pick a coin, in the next stage you toss the coin repeatedly. So you observe the toss and then you ask the question of what happened in the first stage. It's a very typical Bayes rule application. You've done so many problems of it. We'll do the same thing here as well, okay? So how do I do it? What is Bayes rule? Bayes rule is telling you probability that p equals 0.25 given the observations S, okay? You use Bayes rule. What do you do in Bayes rule? Equals probability of S given p equals 0.25 times the probability that p equals 0.25 divided by probability of S. So this is the classic Bayes rule, right? So what is Bayes rule? Probability of A given B equals probability of B given A times probability of A divided by probability of B. And this is all that has been used here. This is all that has been used. This is A given B. Think of this as A, think of this as B, and just use the formula. Okay, B given A, probability of A divided by probability of B. Okay, that's all that's going on here. So now once you write like this, all these terms are quite easy. Okay, so this P of S I will come to a little bit later. Okay, so we'll come to it a little bit later. But probability of P equals 0.25, this guy is just 0.5, right? Because P is uniform 0.25, 0.75. So this is just 0.25. And what about this guy? Given the probability of heads is 0.25, what's the probability that you will observe? Probability of 1 is 0.25. What's the probability you will observe S? So that is, 1 got observed 3 times, so I need 0.25 power 3, and 0 got observed twice, so you got 0.25, 0.75 squared. Okay, as simple as this. This is just typical Bernoulli, repeated Bernoulli calculation, right? Once you know the probability of 1 is 0.25, you can find the probability of S, right? S given P equals 0.25 is simply 0.25 power 3 times 0.75 squared. So you get this, okay? So how do you find P of S? I will come to it in a little while. It's also quite standard, okay? So before you find P of S, it's good to find this guy, probability of P equals 0.75 given S. Again, you use Bayes rule, the same Bayes rule, okay? So you use Bayes rule again. Okay, and you get the same expression except that because it's 0.75 for probability of 1, you will get 0.75 power 3 times 0.25 squared times 0.5 divided by P of S. So what is this P of S? How do you find P of S? It shows up here in both places. How do you find P of S? And that's not very hard, right? So P of S is just so this is S equals S and P equals 0.25 or S and P equals 0.75. This is just the total probability law, and these two are mutually exclusive. So you put in this guy and then this guy, you get the answer. Okay. So now this these two are you pick 0.25, that probability is 0.5, and then you do S given P, and that comes from this guy. So it's the same thing. So it's a typical Bayes rule calculation for finding P of S. So you can add this up. If you add this up, in these two terms, just for simplification, you can do it numerically. I'm just doing it a little bit differently. So you can take 0.25 squared common, 0.75 squared common, 0.5 common. You will get 0.25 plus 0.75. that will just become 1, right. So, it is just 0.25 squared into this. So, you plug it back in here, put in the value of P of S here, you will see that 0.75 squared will cancel, 0.5 will cancel, you just get 0.25. Same thing you put here, you will get 0.75. So, okay, it is a simple calculation, it's basic Bayes rule, nothing has changed from your 2 urns and picking of the marbles and things like that. It is the same thing, it's except it is put in a different context. There are 2 possible types of coins, 0.25 probability of one, 0.75 probability of one. You pick one and then you toss 5 times, you got 1 0 1 1 0, and then you use Bayes rule to find the probability that what could P have been, what is the probability that I got came from one type of coin, or the probability that I got another type of coin given that I observed 1 0 1 1 0. Very standard Bayesian estimation problem. Notice how it was crucial to assume that this P is a random variable, so that you can use probability and all these things very neatly. Now, what do we do for estimation? Now, one estimator, okay, so I made a mistake here, sorry about that, this should be S. Okay, I hope it's clear. Okay. So, one way of doing an estimator is, I will compare these 2 probability. What is the probability that P equals 0.75 given S, and what is the probability that P equals 0.25 given S, which is bigger? Whichever is bigger, I will estimate it to be that. So, that is one approach to deciding an estimator, right. So, you can say P equals 0.75 given S is greater than probability that P equals 0.25 given S, I will estimate it as 0.75. Okay, so, this is strongly using the distribution of P, right. So, 0.25 and 0.75, it uses the distribution of P and does it. Another very popular approach is something called the posterior mean. Okay. So, what are all these words, posterior, this, that, we will see what these are soon enough. But the estimator 2 is much more popular than the first one. It is called the posterior mean and you take the posterior mean of the 2 probabilities. Instead of saying which is greater and picking that one value, I will take the expected value of the posterior distribution. So, P equals 0.25 given S, sorry about that, this should be S. Okay. So, 0.25, so this posterior mean P hat is 0.25 times probability that P equals 0.25 given S plus 0.75 times the probability that 0.75 given S. This is some sort of an expected value. Okay, so this is an expected value, right. So, you can see how it is an expected value. It is called a conditional expected value because you are conditioning on S. Okay. So, we did not look at these kind of expected values earlier, but this is the first time we are meeting something like this. So, you have conditioning on S and then you take 0.25 times probability. So, as far as conditioning is concerned, it is just this another distribution. So, you are taking expected value of a new distribution, 0.25 times probability P equals 0.25 given S, 0.75 times the probability that P equals 0.75. So, you get a 0.625. So, now this value is different from our assumption of the distribution of P. It is neither 0.25 nor 0.75. Okay. So, remember again, the assumption of the distribution on P is like a tool that we are using. It's some rough idea. So, the estimated value that you get for P hat need not be one of the values that you assumed in the prior distribution, in the uniform distribution that you had. Okay. So, these kind of interesting differences will come, but that is nice that you got a 0.625, which is, it seems okay, right. When you look at 1 0 1 1 0, 0.625 looks a little bit more reasonable than 0.75. Maybe, right. So, 3 out of 5 are ones. So, maybe 0.625 is a little bit more reasonable, maybe it is not as strong as 0.75, who knows, no, this depends on the case. Okay. So, this is a typical Bayesian estimation approach. Okay. So, you assume that the unknown parameter has some distribution and then you use simple Bayes rule. Okay. So, you have this 2 stage, the unknown parameter is first chosen and then the samples are generated. So, you have a typical Bayes rule situation. You observe the samples, what is the probability that the unknown parameter was something. So, you have that calculation of this inverted conditional probability using Bayes rule, and then you do this posterior mean, which is all the values that the random variable can, the parameter random variable can take, multiplied by the probability of observing that that particular value conditioned on all the samples. That is the posterior mean. You get an estimate. Okay. So, the posterior mean is much more popular but even the first one is okay. It's called the mode of the distribution, the first one. Okay. All right. So let's look at one more example. I want to point out one more example, just to show you how things can go wrong. Okay. Supposing I change my distribution on P. Okay. More than things can go wrong, how things can vary depending on the distribution you assume for P. Okay. So in the same example, I'm saying Bernoulli P samples. Okay, IID Bernoulli P, nothing has changed. But now the distribution I'm going to assume for P is not uniform anymore. Previously I said 0.25, 0.75 uniform. Okay, that itself sounded a bit arbitrary. So here I'm making an even more arbitrary change to the distribution. I'm going to say the prior distribution. This kind of distribution is called the prior distribution. So I'm going to pick the prior distribution for P as something, right? 0.25 with probability 0.9, 0.75 with probability 0.1. Okay, so this is how I'm picking P. Let's see what happens. How does it change? How does everything change? Let's say we have the same samples, 1, 0, 1, 1, 0. Same notation as before. We estimate using Bayes rule. You do the same calculation, you will now get probability that P equals 0.25 given S to be equal to 0.75. Okay, and probability that P equals 0.75 given S to be equal to 0.25. Okay, so notice how the probabilities have switched. You can check this calculation out. You can see that this is how it works out, and probability of P equals 0.25 given S suddenly became 0.75. So because I changed the distribution for P, the probabilities are changing around here. So because of that, the estimator 1 now is going to say 0.25 instead of 0.75 for P. Okay, so notice how the probabilities have suddenly changed because I changed the initial distribution I assumed for P. So the initial distribution I assumed for P is going to be crucial. Even if you do the posterior mean, you do this calculation, you will get 0.375. Okay. So what's the moral of the story? The moral of the story is this: assuming a prior distribution for the unknown parameter seems like an interesting idea. You're able to easily use Bayes rule. It's an obvious Bayes rule case. You're able to use Bayes rule and you're able to get an estimate. This seems to be a very logical, simple method. But the dependency on the prior seems very strong. Okay, so you change the distribution on the parameters, your estimate is changing. Okay, so one needs more care. One needs to look at the situation very carefully, figure out why you want to choose a particular prior. Is the prior justified? Okay, so all these things one needs to debate, and it's very important to consider these things very, very closely. But the central approach for Bayesian estimation will remain the same. You assume some distribution for the unknown parameter, use Bayes rule, derive the estimator as a posterior mean in most cases. Okay, so let's keep proceeding. We'll study this more closely. So I'm going to put what we did in the previous two examples in a general framework with some notation, which is a bit different than before. There will be one small modification I'll make to the notation to bring in clarity. Notice, I'm going to say x1 to xn is IID according to capital X, and it has a parameter which is capital theta. This is actually, if you haven't seen this before, this is capital theta. This is not small theta, capital theta. Okay. Now, this capital theta is a random variable. It's going to have its own distribution, and that's called the prior distribution. Okay, so the prior distribution of theta. Prior in some sense is before, earlier. Okay, so prior distribution of theta, and this theta will have some distribution. I'll say it's described by f theta of theta. This could be, it could be a PMF or a PDF. Typically PDF, it's very common to use PDF because it's common to assume this theta as a continuous random variable. In the previous examples we saw, we assume theta as a discrete random variable. You could do that also, in which case this will be a PMF. Otherwise, you will have a PDF. Okay, so this is the setting. Okay, so this is a typical Bayesian setting, right? You first pick one, make one random choice, then based on that you make another random choice and you observe something. And then you ask the inverted probability question. Given that I observed this, what's the probability that my first random choice was something? So, okay, it's a typical Bayesian setting, so you can use Bayes rule to invert and find it. Okay, so I have samples x1 through xn, small x1 through small xn. I will use this notation S to denote that I observed these samples. X1, capital X1 equals small x1, capital Xn equals small xn. Now comes Bayes rule. Bayes rule says posterior is proportional to likelihood times prior. Okay, so this is a good way of remembering Bayes rule. How do we write it? Probability that capital theta equals small theta given the samples S is probability of samples given capital theta equals small theta times the prior distribution divided by the total probability of the samples. Okay, so maybe I should write something here. So this is called the posterior probability, posterior distribution. This is called the likelihood. Okay, so we've seen this before, right? This is where we saw maximum likelihood also, right? You find the likelihood, probability of actually observing these samples for a particular theta, right? So this condition theta equals theta is just once you have a particular theta, small theta, what is the probability that you observe these samples? That's exactly likelihood. This guy is prior. Okay, so this is some sort of a normalization. This will show up here. Okay, typically this normalization is not too crucial, but it can be important. I mean, in some cases, in very large cases, this normalization will be a non-trivial factor, but usually in the examples we see so far, the normalization is not too critical. That's number one. The second thing is this normalization does not depend on theta. Okay, it is sort of integrated over theta. So it's marginalized. Theta gets marginalized out, integrated or added over theta. So it does not depend on theta. So that's a critical thing to observe. So that's why people write this proportionality. Posterior is proportional to likelihood times prior, and this normalization can be dropped, because if you vary theta in this equation, P of S does not change. It remains the same because it's been added up over all theta. Right? That's how you find P of S, right? So if you want me to write it down very clearly, P of S equals, so if you have in the discrete case, P of S is summation over theta, P of S given theta equals theta times F theta of theta. Okay, let me write this down carefully. And in the continuous case, you will have P of S being integral over theta, P of S given theta equals theta times F theta of theta d theta. Okay, so theta sort of disappears from this P of S. You integrate it out, some over all possible values. So because of that, the normalization is the same. So in some cases normalization may be important, but if you're just comparing different values of the posterior, it's not very important. But if you're finding the posterior mean, then this P of S becomes important. Okay, so it's important to keep that in mind. Okay, so this is how this equation looks. It's the same as what I did in the example, except that I've written it in a more general framework. Okay, but this rule is important to remember. Bayes rule, posterior is proportional to likelihood times prior. Likelihood is also important, prior is also important. Okay, if you do maximum likelihood estimation, there's no prior or posterior or something, there's only likelihood. Now you bring in a prior and you multiply with the likelihood. Okay, so you do estimation using the posterior probability. Probability of theta given S is what you use. Okay, so you can use the posterior mode if you want, which will simply set theta hat, your estimator, to be argmax of probability of theta equals theta. So this is like, remember, this is the same as argmax over theta of probability of theta equals theta given S. Okay, why is that? Because so these two are proportional. This P of S does not depend on theta. So if you're maximizing the left hand side here, it's the same as maximizing this quantity. Okay, likelihood times prior, you maximize that. So that's posterior mode. You might want to pick the mode, but it's much more common to pick the posterior mean as the estimate. Okay, so theta hat is expected value of this theta given S. Okay, so mean of the posterior distribution. Okay, so how do you write it down? So if it's in the discrete case, the mean is going to be simply summation over theta times probability of capital theta equals theta given S. So that's what this means in the discrete case. In the continuous case, you'll do an integration. Okay, theta times probability of so this will be a density, posterior density. Okay, So we'll see some examples. I'll show you some examples. You'll see. Okay. So in this case, I put probability of theta equals theta given S. In the posterior case, it will be the posterior density, right? So when you do the integration, you don't write P off. So you put the density of that conditional density, and then you will get it. Okay. So this is the posterior mean. So we have a conditional expectation here. There's a conditional random variable theta given S, and then you're taking expectation of it. So I showed you how this was done in a couple of examples. Okay. So this is the setting of Bayesian distribution. Okay, so the meaning of the prior distribution causes a lot of confusion among thinking of how to do Bayesian, etc. We also already saw examples where if you change the prior, the estimate is going to change. So what do? You keep on changing the prior, you'll get different estimates. Which one do you take? Is there a meaningful prior? Is there a set way to pick a prior? Are some priors allowed, some not allowed? All these are very valid, interesting questions. So generally, from a general philosophy of use point of view, the prior distribution could come because we know something about the unknown parameter. Like for instance, if the parameter is Bernoulli P, then you know P lies between 0 and 1. Okay, so you may want to use that in the prior distribution. Okay, or it may, the prior distribution, the parameter may be something scientific. It might be the temperature of a day, or things like something else which is scientific, or maybe resistance, or voltage, or something, some engineering, technological, scientific term which is constrained by physical laws. So based on the physical laws, you may be able to say something about the prior distribution. So that also is possible. Okay, so prior distribution can be informed by domain knowledge, scientific models, and other things. Okay, so the most interesting relationship in the Bayesian setting is that the posterior distribution is proportional to the likelihood of the samples times the prior. Okay, so likelihood times prior is posterior. So this is sort of an interesting viewpoint of how using the data, you have a prior distribution without using the data. Right? Data didn't play a role in the prior, you just came up with a prior. Then once you saw the data, how do you update the prior distribution and get a posterior distribution? So this kind of thinking is useful in modeling. So you can use a lot of information from the data itself, some part of the data, to do some modeling and come up with some interesting models. Okay, so what if we don't have any scientific basis? What if we don't have any domain knowledge? We're just looking at numbers. Then usually people will pick a flat distribution over the range of possible values. Okay, so a range of possible values for your unknown parameter, simply pick a flat distribution. So then you're not putting any undue emphasis on any one part. So it becomes an interesting way of going about doing the design. Okay, so you'll see there'll be lots of fights and debates between frequentists and Bayesians. Frequentists will say using a prior is nonsense. Bayesians will say not using a prior is totally meaningless because it's quite useful in many cases, etc., etc. But the way I look at it is just one more method for coming up with an estimator, and any estimator can be useful in some situation or the other. Okay, so that's a quick summary of Bayesian setting, and we'll close this lecture at this point. Hopefully, the philosophy of how to come up with Bayesian estimation is clear. So we're going to see a few examples of how to come up with priors, how to do Bayesian estimation in the next lecture. Thank you.